Okay, the periodic table, the periodic law. So in 1869, Dmitri Mendeleev noticed that certain groups of elements had similar properties. Mendeleev is often given credit for being the father of the modern periodic table. There were other people, it's debatable, but we're going to go with what the book says. So he found that when he listed the elements in order of increasing mass, similar properties recurred in a periodic pattern. Periodic means that it exhibits a repeating pattern. You go to the library and they have a periodical section. Periodical section has monthly magazines, weekly newspapers, weekly magazines, daily newspapers. It's publications that come out on a regular basis. So here's an example here. So if we take the first 20 elements and list them in order of increasing mass, he noticed that hydrogen, orange, fluorine, orange, and chlorine, orange, had some common properties. They weren't exactly the same, but they had some similar characteristics. Helium, neon, and argon had similar properties. It's a little bit like a piano keyboard, where if this is middle C, this is C 1 octave above, and another C 2 octaves above middle C, right? And if you play all three of those notes together, they are harmonics of the same note. Okay? So this is called the periodic law. It's an observation of what is, doesn't explain. It says when the elements are arranged in order of increasing mass, certain sets of properties recur periodically. So he organized the elements that were known at his time in a table instead of one long list. And he made the table so that he stacked elements with similar properties in columns. You'll notice that hydrogen is over here, even though it's orange. Hydrogen is the smallest element. I think of him as the baby brother of the overall element family. And we all know what happens with that youngest child, right? They get away with all kinds of stuff that the first, the second, third born would never get away with. I think it's because mom and dad are old and tired, and they realize that some of that stuff just doesn't matter anymore. I have a hydrogen in my house. His name is Andrew. Anyway, so hydrogen is going to be an exception to all kinds of things. So when he's an exception, we just say, that's hydrogen. But the rest of these, we see that they stack up very nicely. And these columns are called element families. And just like children in the same family, siblings, have some things in common, so do these elements. A set of siblings are not identical to each other, right? I suppose you could say that identical twins are like isotopes of the same element, but just talk about regular siblings. They're not exactly the same, but they have some things in common, right? So the table that Mendeleev made had some gaps in it because he could only work with the elements that he knew about. They hadn't all been discovered yet. So he left some gaps because that's what made sense with organizing the properties. And he predicted that elements would be discovered to fill in the blanks. And they were. He predicted the existence of an element that he called ecosilicon. Eka means below. So this was an element that would fill in the gap below silicon, where there was a gap. And not too much later, 1886, that element was discovered. A German chemist named Clemens Winkler. He named it germanium after his home country. Mendeleev also predicted some of the properties of these elements, and he was remarkably accurate. So here's a different type of periodic table, giving us the time of discovery for the different elements. This is just for our interest. You would not ever be tested on anything like this. But here we see silicon. So silicon was known between 1800 and 1849. Germanium was not. That wasn't discovered until later. But Mendeleev left a gap there in his table predicting that that would happen. And down here, these are all elements that have been discovered or made much more recently, since 1950. Any questions? And this is how, in 1869, Dmitri Mendeleev completed his first periodic table. It's Tetris. So in the modern periodic table, instead of increasing mass, they are listed in order of increasing atomic number. Most of the time, that gives the same ordering, but there are a couple of exceptions. One of them is element 52 and 53. So tellurium has fewer protons, but its mass is larger. And the atomic number is actually the ordering property, not the mass. Here's another periodic table. There are so many different ones, and they all have basically the same elements and everything, but some of them have extra information. This one has some nice little pictures showing us pictures of some of the elements. But what I want to point out to you in this one is there's a stair-step line here, right? And that's on the periodic table on the wall. It wasn't originally, and we like that line, so we put it up there with blue tape. The periodic table I give you for exams will have that line on it. That is the dividing line between the metals and the nonmetals. The upper right corner is the nonmetals, and the lower left side is the metals. And again, we see hydrogen being an exception. He's a nonmetal, but he's over there hanging out with the metals because he wants to, I guess. How do you remember which side is which? Well, think of an element that you know something about. How about oxygen? We've all heard about oxygen. We know that we need that to breathe. Is oxygen a metal? No, that would be crazy. Oh, well then these must be the nonmetals. Over here, iron. Is iron a metal? Yep. So this whole group, all of those guys are metals. The ones that are directly touching the line here in the purple are called metalloids or semi-metals. They are in this dividing line between metals and nonmetals. They're kind of like teenagers. They're not teens, but they're not really children either. They're kind of in between. And so these have properties that are in between. The exception is aluminum and polonium. I don't care about polonium because he's really rare and we're not going to run into him. Aluminum, though, we'll do a lot of stuff with aluminum. Aluminum is touching that line, and yet, is aluminum a metal? Yeah. Think of a metal cookie sheet. It's probably made out of aluminum. Aluminum is definitely a metal. So you should know that aluminum is a metal. And then anything else that shares a side with the line, call it a semi-metal. We also see that we have some numbers here on the left. Those are period numbers, row numbers, and those come in useful sometimes. And then we have group numbers. So each of these columns has two numbers at the top. The 1A, 2A, the set above, is what we currently use in the United States, and that's the ones I'm going to use mostly. The numbers below, just 1 through 18, that's what the International Union of Pure and Applied Chemistry has decided that they should be numbered. But they're not going to come and check what we're doing, so we're going to use the current U.S. usage and use these with the A's. Another interesting thing is we see this arrow here, and this row is called the lanthanides, and then we've got the actinides. If you look at the atomic numbers here, lanthanum is 57, and next to it is hafnium, 72. That's not in order, is it? That's because from 57, you need to come down here to cerium, continue through these, I think that's lutetium, 71, and then back up to 72. So really the periodic table, we should take a pair of scissors, cut it there, and insert these. That's what we have on the wall, not because that's how it should be, but that's because it fits on the wall better because we don't have enough space up there. But that's the true shape of the periodic table. We don't use that on paper very often because it's really long and skinny and it doesn't fit on a piece of paper very well, or a screen, or a page in your book. These guys are unusual, and so we just kind of took them out and stuck them at the bottom. They're there if we need them, but most of the time we don't. This row is called the lanthanides because they come after lanthanum. This row, again, I'm having trouble with my pointer, is called the actinides because they come after the element actinium. Any questions? So we classify elements as metals, nonmetals, and metalloids. I showed you where they are on the periodic table. These are the general characteristics of these different types of elements. Metals conduct electricity and heat. They're malleable. You can pound them into sheets. They're ductile. You can draw them into wires. They are often shiny. And what's important for chemistry is they tend to lose electrons when they undergo chemical changes. So they lose electrons. If an atom loses negatively charged electrons, what kind of an ion does it form? A cation or an anion? A cation. Losing negative charges gives the ion a positive charge. So metals form cations. Nonmetals are not metals, right? They're kind of just like whatever a metal is, then a nonmetal is not that. They don't conduct well, they're not ductile, they're not malleable, and instead of losing electrons, they gain electrons. So they're like, opposites. They gain electrons. So if they're gaining electrons, they're gaining negative charges. Nonmetals form anions. So I think of it this way. Nonmetals form negative ions. Nonmetal, negative. Metals form positive ions. I also think about metals as being more masculine and nonmetals as being more feminine, but that'll come in later. Just a little teaser for the future. The metalloids or the semi-metals have mixed properties. They're kind of both and neither at the same time. Some of them are semiconductors, and those are really important for computers and other sorts of technology like that. They have an intermediate electrical conductivity that can be changed. And so that's how we can make computer chips. And, if it weren't for semiconductors, you would not have a cell phone that could do all these amazing things. Another way to divide up the periodic table is main group elements and transition elements. So I think of the main group, so this part sticking up here and this part sticking up here, as being like a land mass, the mainland, right? Here's the banks, right? And it's even blue. This just occurred to me yesterday, by the way. This is even blue. This is like the water in between. It's the transition from this bank to the other bank. So these are the transition elements, and the parts that stick up are the main group elements. And that's significant because main group elements are more predictable in their properties, and transition metals elements are less predictable, and so we will sometimes refer to main group elements or transition elements. We need to know which ones they are. This also identifies that these are the periods and those are the group numbers. 4 of the groups in the periodic table have names. The noble gases is group A, 8A, sorry. They're all most of them are group A. Noble gases are group 8A. They're very unreactive. The alkali metals are group 1A, and those are very reactive metals. The alkaline earth metals are group 2A. They're fairly reactive, but not as much so as the alkali metals. And then we've got the halogens, group 7A. Very reactive nonmetals. So over here, these are the alkali metals, the alkaline earth metals, the halogens, and the noble gases. Because sometimes it's easier to refer to them as a group than trying to name them all. It's like, oh yeah, it's one of those Kawagoa kids. So the ions that the main group elements form are mostly predictable. So if we look at the main group metals, they tend to lose electrons like all metals do. They form a cation, and they form a cation that has the same number of electrons as the nearest noble gas. And I'll show you in a minute what that looks like. The main group nonmetals tend to gain electrons, and they form anions. They form anions with the same number of electrons as the nearest noble gas. So we need a periodic table. So these are the noble gases. I think of those as being like that cool group of kids in high school. The one that, everybody else was trying to be like them. And what do students do when they were trying to be like someone they admire? They dress like them, right? They get their hair cut the same way, they style it, they start to walk the same way, right? It's really interesting once you're out of high school to look back at high school and realize that they're all trying to be so individual, and yet they're like copying each other, and there's a remarkable amount of uniformity. It's really interesting. But, I was there too, did it too, everybody does. So this is what everybody wants to be like. And I said that electrons are like the clothing for the atoms, right? So here's fluorine, and fluorine would like to look like neon, but he only has 9 electrons. So fluorine can look like neon if he puts on an extra electron. Oxygen can look like neon, but it has to put on 2 electrons. Nitrogen has to put on 3 electrons. What about carbon? Carbon's like 4 electrons? Too much work, not going to do it. He's one of these guys that's just happy to be a nerd. It's like, you know what? It's so hopeless, I'm just not even going to try. I'm just going to be what I am. And he's probably the happiest of all of them. And then we look at the metals over here. Sodium has 11 protons, 11 electrons. Sodium wants to look like a noble gas also. Well, the closest noble gas is actually going backwards over here. Where's my pointer? And having issues with my pointer, that's what I was doing. So there's sodium. Sodium has 11 electrons. If sodium wanted to be like argon, it would have to gain 7 electrons. That's an awful lot. Or it could just take off 1 electron, and it would have the same number of electrons as neon. So that's easier, and that's what it does. You can think of, and I actually have one that I made in my office. I should have brought it. You can actually think of this periodic table as more of a spiral. If you cut this out and tape it together, because this is 1, 2, and then it comes over here to 3. And so it's really just a spiral. So we think of sodium as being next to neon. A little bit like the globe, right? You got to cut it somewhere, but we know that it's not flat. And the east and west actually do meet up. Okay. So the alkali metals, group 1A, tend to lose 1 electron. They form 1+ ions. So group 1 plus 1. The alkaline earth metals, group 2, tend to lose 2 electrons. Form +2 ions. Group 2 plus 2. That's nice. The group 7A elements, the halogens, tend to gain 1 electron. So they form a 1- ion. And the oxygen family that doesn't have a name, group 6A, they tend to gain 2 electrons and form 2- ions. So ways to remember this, for the main group elements that form cations, the main group metals, the charge is equal to the group number. Group number 1 plus 1. Group number 2 plus 2, and there's a couple in group 3 plus 3. So that's nice. The main group elements that form anions, the nonmetals, one way to do it is say the charge is equal to the group number minus 8. So group number 7 minus 8 equals -1. If you like that, use it. If you don't, I've got another thing. And then those transition elements, not predictable from the periodic table. We'll talk about those in a future chapter. So here we have the group 1 metals. They all form +1 ions. So when we write the symbol for the ion, we always include the charge. This is different than math. Okay, so if you have x to the +1 power, you just write x, right? And if you have x squared, you don't put a sign on it unless it's negative. But we always write the sign for ions. And we put the number first and then the sign. If it's only 1, we don't write the 1. We'll see there are lots of places where we leave the 1s out because we understand that they're there, and we're actually trying to make this more concise with less writing. So these guys form 2+ ions, losing 2 electrons. And you see that hydrogen's over here acting like a metal. That's one of the reasons they stick him over there on the periodic table, because he also loses an electron and forms a +1 ion. And then there's aluminum, and aluminum will lose 3 electrons to become like the nearest noble gas. Aluminum is a metal. In group 3, it forms a 3+ ion. So metals in the main group, the charge equals their group number. That's not too bad. So here are the noble gases. They don't do anything because they are just so cool with themselves, right? They're not going to change how they look for anybody. Right next to them, the halogens, and we can also sometimes put hydrogen over here. These are going to gain 1 electron to look like a noble gas in terms of number of electrons. So you can take the group number 7 minus 8 and get -1. Or what seems to work better for students is, let's think of this as a weird board game, and the noble gas is the starting point. And whatever element you're trying to figure out the charge for, you count backwards. So if I'm looking for nitrogen, I'm going to start over here in the noble gas column, and I'm going to count backwards. -1, -2, -3. So nitrogen is going to have a 3- charge. Phosphorus is right below it. There's phosphorus. What charge would a phosphorus ion have? 3-, because here's 0, -1, -2, -3. So we'd write 3-. So all of these form -1 ions. All of these form -2 ions. Tellurium is a semi-metal, but it also participates here. And all of these guys form -3 ions. This column 4 just doesn't really do ions. It's just carbon and silicon, and they're like, it's hopeless. How do you determine whether it's positive or negative? That's a great question. All of the nonmetals on this side of that line will be negative. Nonmetals are negative, and all of the metals are going to be positive. Okay, so that's one way. That's just like a how to remember. The reason these are positive, because the easiest way for them to have the same number of electrons as a noble gas is to just lose 1 or 2, or for aluminum, 3 electrons. For the nonmetals, they would have to lose an awful lot of electrons to go to the previous noble gas. It's easier for them to gain an electron and become like a noble gas. So that's why they form negative ions. So yeah, carbon really, for our purposes in this class, carbon doesn't make ions. I am going to lie to you sometimes. It's for your own good. There are some things that are just beyond the scope, and it would take way too long to explain to you, and you wouldn't like it anyway. So yeah. We're just going to go with nonmetals are always negative ions. Metals are always positive ions. What we'll see is these transition metals, their charges are not predictable from the periodic table. So predict the charges of the monoatomic ions formed by these main group elements. Monoatomic means that it's a single atom making an ion. So what would the charge on nitrogen be? -3, right? So we would write the symbol for this as N3-. And how do we know that? Because here we find nitrogen, and we start over here and we go -1, -2, -3. Always nitrogen. We'll get to a chapter later that explains why nitrogen does that, but for now we just need to know that it does. And then rubidium. So rubidium is right here. What kind of an ion? +1. All of these in group 1 form +1 ions. So for its ion symbol, we'd write rubidium with a positive sign. Any questions?